Hey everyone, and welcome to The Explainer. I am absolutely thrilled to have you here today. You know, every business owner, whether they're running a little local coffee shop or a massive tech manufacturing plant, literally loses sleep over three very specific economic curves. Honestly, understanding them is often the difference between thriving and going totally bankrupt. So today we're diving into a visual masterclass. We are going to completely demystify the behavior of short-run total costs. If you've ever looked at a business's cost structure and just felt totally overwhelmed by all the moving parts, well, you're in exactly the right place. We're going to decode the whole shebang using a single, highly logical graph. By the time we wrap up, you'll be reading that graph like a seasoned economist. Here is our roadmap for today. We'll start with the foundation of short-run costs. Then we'll move on to tracing out total fixed cost and total variable cost. After that, we'll derive the total cost itself, and finally, we'll tie it all together with the law of variable proportions. All right, let's jump right into part one, laying down the foundation of short-run costs. The big concept we're tackling today revolves around one overarching equation, total cost. Total cost, or TC, is exactly what it sounds like. It's the total expenditure a business incurs to produce a given amount of output. It accounts for absolutely every type of input. To really make this concrete, imagine for a second that you're running a boutique chocolate factory. Your total cost is the entire financial weight of keeping that operation running every single month. And the math here is beautifully simple. Total cost equals total fixed cost plus total variable cost. TC equals TFC plus TVC. That little equation right there, that is the absolute bedrock of the visual derivation we are about to explore. Now, to really grasp how that equation works, we've got to contrast its two main ingredients. Let's go back to our chocolate factory. On one side, we've got fixed costs. These are incurred on fixed factors, meaning they are completely independent of your output. Think about the rent for the building, the interest on your factory equipment loans, or your property taxes. The simple, kind of harsh reality of business is that your landlord doesn't care if you didn't sell a single chocolate bar this month. That rent is absolutely due. That's why we call them unavoidable costs. On the flip side, we have variable costs. This is the dynamic engine of our cost structure. These costs vary directly with the volume of your output. They go up as you produce more, and they drop as you produce less. We're talking cocoa beans, sugar, the electricity to run those big industrial mixers, or the wages for your seasonal workers. If production completely stops, these costs instantly drop to zero, making them avoidable costs. Okay, let's set up our canvas. Whenever we map out economic behavior, we need our coordinates, right? On the horizontal x-axis, down at the bottom, we're measuring output, literally how much chocolate our factory is actually producing. On the vertical y-axis, we're measuring cost, how much money is being spent to make that chocolate. Everything we discussed today is going to live right here in this space. Moving right along to the second step, tracing out that total fixed cost. Take a look at how incredibly flat this TFC line is. It's just a straight horizontal line perfectly parallel to the x-axis. But really pay attention to where it begins. It originates at point A on the vertical y-axis. This visually proves a critical concept. Even if your output on the x-axis is completely zero, meaning the factory doors are locked, the lights are off, zero chocolate is being made, your total fixed cost is still a positive amount. It's represented by that distance OA. And it remains constant at that exact amount at every single level of output moving to the right. This is the defining characteristic of what economists call the short run. You are locked into certain fixed obligations, and there's absolutely nothing you can do about it right now. Next up, part 3, let's trace the total variable cost. But hey, before we draw this next curve, I want you to think about something. Why on earth would the total variable cost curve completely change its shape right in the middle? It doesn't just shoot up in a straight diagonal line. It entirely shifts its behavior. Keep that question floating in the back of your mind as we reveal the curve. All right, here is our TVC curve. Let's trace its path step by step. First off, it starts directly at the origin, 0, which makes perfect sense for our factory, right? If you're making 0 chocolate bars, you're buying 0 cocoa beans. Your variable costs are 0. But watch its trajectory. Initially, it's concave downward. In economic terms, this means the total variable cost is increasing, but at a decreasing rate. It's climbing, sure, but the climb gets a little gentler. Think of your factory just starting up for the day. You hire a few workers, they start coordinating, the machines get warmed up, and everything runs incredibly smoothly. But this golden phase of efficiency, it only lasts up to a specific level of output, marked right here as OQ on the x-axis. Beyond point OQ, the curve suddenly flips. It becomes concave upward. From here on out, the TVC is increasing at an increasing rate. Basically, chaos starts creeping in. As you try to squeeze more and more chocolate out of the exact same factory space, your costs start accelerating way faster than your output. Okay, part 4. This is where we derive the total cost. We are going to visually build this total cost curve right now. Remember that TC equals TFC plus TVC equation? Well, to do this on a graph, we literally just add the curves together vertically. Step 1, we absolutely have to start the TC curve at point A on the y-axis. Why? Because at zero output, TVC is 0, leaving only those fixed costs. Step 2, at every single point of output moving right, we visually stack the value of TVC squarely on top of the value of TFC. Step 3, because TFC is completely constant, this stacking means we must maintain a perfectly uniform vertical distance between the TVC curve and our brand new TC curve. Look closely here. The TC curve does not start at 0. It originates precisely at point A. Again, because when output is 0, your total cost is exactly equal to your total fixed costs. Your variable costs just haven't kicked in yet. The starting points align perfectly to show us this reality. And this right here perfectly illustrates that vertical addition we just walked through. Guide your eyes to those vertical arrows located squarely between the TVC and TC curves, labeled TFC. Because the rent on our hypothetical chocolate factory literally never changes, the gap between what it costs to make the product, the TVC, and the overall total cost, the TC, remains permanently locked at that exact distance. That vertical gap never shrinks, and it never expands. It is exactly the same at every single level of output. The TC curve is basically just the TVC curve shifted upward by the exact, unchanging weight of those fixed costs. Finally, part 5. Let's talk about the law of variable proportions. Let's do a quick recap of the distinct behavioral phases we just mapped out. Both the total cost and the total variable cost curves start off by increasing at a decreasing rate. That's that concave downward shape. Then, beyond a certain output level, they both suddenly switch gears. They begin increasing at an increasing rate, taking on a concave upward shape. And because they are separated only by that constant, flat, total fixed cost we talked about, their overarching shapes mirror each other flawlessly. So what's actually causing this? Why the dramatic shapeshifting? It is entirely due to a foundational economic concept known as the law of variable proportions. Let's bring it back to the chocolate factory one last time. In the short run, you have fixed inputs, namely the physical square footage of your factory building and those big mixing machines bolted to the floor. As you start adding variable inputs, like hiring more chocolatiers to that fixed space, you initially get this massive burst of efficiency. People specialize, right? One person melts, one pours, one wraps. Your costs rise, but they rise slowly. That is your concave downward phase. But eventually, you hire way too many people for the space you have. The factory gets incredibly crowded. Adding more workers actually becomes counterproductive. People are bumping elbows on the factory floor. They have to literally wait in line to use the mixing machines. The machines themselves start breaking down from overuse. You hit diminishing returns. Because everyone is less efficient, it suddenly takes increasingly more resources, more hourly wages, more wasted cocoa, just to produce one more single chocolate bar. That steep drop in efficiency is exactly why your variable and total costs suddenly accelerate, forcing both curves to become concave upward. To wrap things up, I want to leave you with something to chew on. If a business can never escape its total fixed costs, as we clearly saw with that flat, unforgiving line, you might logically think, hey, the primary goal is just to produce as much as humanly possible to spread those costs out, right? But based on what we just learned about the law of variable proportions, how can blindly maximizing output actually lead to a business's downfall? Just picture that accelerating concave upward curve at those really high production levels. The chaos on the factory floor eventually becomes way too expensive to sustain. It forces businesses to carefully, mathematically balance their production, proving that bigger really isn't always better when your efficiency inevitably starts tanking. Thank you so much for joining me on this deep dive into short-run costs. Keep exploring, keep questioning, and I'll see you next time.